It is March 1945, somewhere in the Rhineland, and a German sapper is watching American engineers work. He is watching them find his mines, by hand. He had been told these charges were undetectable. He had been assured, by the engineers who designed them, by the procurement officers who approved them, by every technical report that crossed his desk, that the materials used in these devices would defeat any instrument the Allies possessed. And on paper that was true. The instruments had been defeated, every single one of them. Yet here are the Americans, on their elbows and knees in frozen mud, pulling mines from the earth as calmly as a man pulling weeds from a garden row. The word the sapper wrote in his field report was Ratlosigkeit. It translates roughly as bafflement, the state of being without counsel, without explanation. He could not understand what he was seeing. To understand it, we have to go back 2 years and 800 miles south. In the autumn of 1943, the Allied advance up the Italian peninsula ran into a wall. Not a metaphorical wall, a literal one. Field Marshal Albert Kesselring had ordered the construction of what the Germans called the Gustav Line, a defensive belt stretching from the Tyrrhenian Sea to the Adriatic, anchored on the Rapido River and the monastery at Monte Cassino. The fortifications were conventional enough. Gun emplacements, bunkers, interlocking fields of fire. But the real weapon was underneath. 300,000 mines, laid in overlapping patterns across every road, every ford, every plausible avenue of approach. And mixed in among them, thousands of buried shell casings, inert, harmless, but identical in shape and weight to the real thing. Every casing had to be investigated. Every investigation cost time, and time, under artillery fire, cost lives. The existing method for clearing a lane through a minefield was a man with a metal detector, sweeping side to side, one step at a time. When the detector chirped, the man stopped, knelt, and probed the ground with a knife. If the object was a mine, he disarmed it, or marked it. If it was a shell casing, he'd wasted 3 minutes. Multiply that by 1,000 false alarms across a single approach lane, and you begin to see the mathematics of the problem. A single battalion could clear perhaps 200 meters of safe lane in a day. Kesselring had planted minefields 4 kilometers deep. The Allies needed a faster way to sort real threats from decoys, and that need arrived by a series of turns that feel almost too neat, on the desk of a man named Marek Dursky. Dursky was Czech, a physicist. He had been at Charles University in Prague before the occupation, and had gotten out, barely, through a chain of colleagues and forged transit papers that eventually deposited him in London in 1940. He was brilliant, he was desperate, and he had a particular reason to care about mines. 9 of his former colleagues, men he had shared a laboratory with, men whose handwriting he recognized on blackboard equations, had been killed when their transport struck a mined approach in a harbor channel. 9. Not in battle, not under bombardment, killed by a device hidden under 60 centimeters of silt, placed there weeks earlier by a man who was probably already dead himself. Dursky understood magnetic fields. He understood that a buried iron casing distorts the Earth's ambient magnetic signature in a way that is small, but with the right instrument, legible. He built a prototype sensor, a magnetic anomaly detector tuned not to the mine itself, but to the way the mine's metal interrupted the field around it. The device was more sensitive than a standard-issue mine detector by a meaningful margin. It could distinguish a 5-kilogram iron casing from a buried rock at twice the range, and it could do it while moving. He submitted the design to the War Office. It passed a competitive trial. And then Dursky did something that tells you who he was. He surrendered the patent, anonymously. He refused to have his name attached to it. The reason was not modesty. His sister and her 2 children were still in occupied Prague. If the Germans connected a Czech refugee physicist in London to a weapon that was killing their sappers in Italy, the family would be taken. So the device went into production under a War Office designation, and Dursky went back to his rented room in Kensington and waited for news. 400 units were manufactured and shipped to the Italian front in early 1944. The effect was immediate. Safe lane output nearly tripled. Engineers who had been spending hours sorting real mines from decoy casings could now sweep a lane and ignore the inert metal with reasonable confidence. The bottleneck cracked. Units that had been pinned behind the minefields began to push through. The Gustav Line did not fall quickly. Nothing in Italy fell quickly. But the math had changed, and the German planners could read a tally sheet as well as anyone. Here is what makes the next part strange. The Germans looked at what had happened. at the sudden acceleration of Allied mine clearance, and they drew a conclusion, a reasonable conclusion, a nearly correct conclusion. They decided that the Allied advantage was the sensor, that the Americans and the British had developed a new instrument, more sensitive than anything the Germans had anticipated, and that this instrument was the thing standing between them and the paralysis they had designed their minefields to inflict. Eliminate the ferrous signature, they reasoned, and you eliminate the edge. It was a sound piece of engineering logic. It was also, in a way that would take 2 years and tens of thousands of casualties to become visible, the wrong question. Because the sensor was not the advantage. The sensor was a tool, one tool, inside something much larger that the Germans had not built and therefore could not see. The Americans were constructing an institution, a system for testing, failing, recording the failure, rewriting doctrine, and training the revision. The sensor was a chapter in that system. When the chapter was made obsolete, there would be another chapter, but the Germans did not know that yet. What they knew was metal and frequency and detection range, and so they set out to build a mine that no instrument on Earth could find. That effort, and the particular kind of genius it required, is where the story turns. Somewhere in the Thuringian Hills, in the autumn of 1943, a ceramics engineer is standing in a factory that 6 months earlier made dinner plates. He is holding a small pale disc, about the diameter of a saucer, perhaps 3 centimeters thick. It is smooth, surprisingly light, and if you pressed your thumb against its surface, you would feel the faint granular texture of fired clay. It does not look like a weapon. That is the point. The disc is the casing for the Erdmine 43, and it represents the German answer to Marek Dursky's sensor, a mine with no metal in it at all. The logic was clean. Allied detectors worked by sensing ferrous metal, iron, steel, anything that distorted a magnetic field. Remove the metal, and the detector has nothing to hear. So the Erdmine 43 was built from precidite, a composite ovatidite, powderydite, andite fired at high temperature into a rigid shell. The detonator used a chemical fuse rather than a mechanical striker. The entire assembly, from casing to charge to trigger, contained not a single gram of iron. A man could pass a detector directly over it and hear nothing but the ambient hum of undisturbed earth. But the Erdmine was not merely invisible. It was cruel by design. The charge was calibrated not to kill the man who stepped on it, but to sever his foot at the ankle. A dead soldier is a subtraction, one man removed from the line. A maimed soldier is a multiplication. He requires 2 stretcher bearers to carry him, a medic to stabilize him, a jeep to evacuate him, a field hospital to receive him, and a bed he will occupy for months. One device, 5 men removed from the fight. The engineering was precise and the arithmetic was deliberate. American engineers on the Rapido River discovered the Erdmine in early 1944, and the discovery was not academic. It was men stepping on objects their instruments had told them were not there. The Mark IV detector, the workhorse of Allied mine clearance, was blind to it. Reports went back up the chain in language that was unusually blunt for official correspondence. The detector, the report said, was useless against this device. The word useless does not appear often in military engineering assessments. Its presence here tells you how bad the situation was. And then the Germans went further. The Porzellanmine 44 arrived in the field by mid-year, an all-ceramic device, manufactured from true porcelain, harder and more uniform than the pressed clay Erdmine. Its fragments, when it detonated, were indistinguishable from shattered rock on a field X-ray. A surgeon probing a wound could not tell mine casing from bone chip. Thousands of men would carry porcelain splinters inside their bodies for the rest of their lives without any imaging technology being able to confirm what was in there. Production was enormous. Germany had, for obvious historical reasons, a large and technically sophisticated porcelain industry. Factories in Thuringia and Saxony that had been turning out tableware and laboratory equipment were retooled with relative ease. Hundreds of thousands of Porzellanminen were produced and shipped to every active front. The device was cheap, fast to manufacture, and against any instrument the Allies had fielded, genuinely undetectable. But the Germans were not finished. Alongside the new casings, they deployed a countermeasure aimed not at Allied instruments but at Allied confidence. Cleared lanes, routes that engineers had already swept and marked as safe, were seeded with magnetized gravel, small iron-rich stones deliberately scattered across ground the Allies believed they had secured. The next patrol through would sweep the lane, hear a dozen phantom readings, and face an impossible choice. Treat every reading as real and slow to a crawl, or assume the readings were false and keep moving. Either outcome served the German purpose. The first bought time, the second bought casualties. Here is what makes that sequence remarkable. Every one of these innovations, the clay casing, the porcelain casing, the magnetized gravel, was technically brilliant. Each one neutralized a specific Allied capability. Each one was a correct answer to the question the Germans believed they were being asked. And every one of them shared the same blind spot. They all assumed the question was, is there a magnetic anomaly here? Because while the Germans were perfecting the art of the invisible mine, the Americans had already begun to abandon the instrument those mines were designed to defeat. The pivot did not come from a laboratory. It came from the field, from engineers who had watched their detectors fail on the Rapido and had needed to clear a lane anyway. The method they fell back on was old. Not old in the way that something from the previous war is old. Old in the way that a stick is old. A man lies flat on the ground. He takes a thin steel probe, a bayonet, or a length of stiff wire, and eases it into the soil at a 30-degree angle, pushing gently, moving it forward in a slow arc. What he is feeling for is resistance. Not metal, not a magnetic signature, just the physical fact that something rigid is buried in a place where the soil, left to itself, would be uniformly soft. The question the bayonet asks is not, is there a magnetic anomaly here? The question is there a rigid object here that the soil did not put there? That question cannot be defeated by changing materials. Clay, porcelain, glass, wood, concrete. It does not matter. If it is harder than the earth around it, the probe will find it. The Germans had spent 18 months and considerable industrial resources engineering their way around a magnetic sensor. The Americans had sidestepped the entire axis of competition by asking a different question, one that could be answered with a piece of steel wire and a patient hand. The Germans did not know this yet. They believed they were winning the detection war. They had in fact won it. The sensors were beaten. What they had not understood, what their intelligence apparatus had not surfaced, and their engineering culture had not been built to consider, was that beating the sensor did not matter if the enemy no longer depended on the sensor. And Germany still held one final secret, a substance called detectors, a barium-laced camouflage powder that would, in theory, make their invisible mines findable again, but only by their own forces. It was, in its way, the most elegant piece of the entire program. It was also the most irrelevant. And that is the part of the story that matters. Picture a German sapper in early 1945, somewhere along the Siegfried Line, kneeling in a field he mined 3 weeks ago. He has a problem. The mines he buried are invisible. Invisible to the Allies, yes, but also invisible to him. The ceramic casings carry no magnetic signature. The ground has settled. Rain has washed away the surface disturbance. He needs to find his own weapons, and he cannot. This is the problem that detectors was built to solve. Detectors, the word translates loosely as cover earth, was a fine powder laced with barium compounds. After a mine was buried and the soil replaced, a dusting of detectors was applied over the site and raked into the surface. To the naked eye, the ground looked untouched, but barium is radiopaque. It stops X-rays. A German sapper returning to the field with a fluoroscope wand, a handheld device that projected a low-intensity beam into the soil, could sweep the ground and watch for the telltale shadow of barium concentration on his screen. Where the shadow appeared, a mine sat beneath. It was, by any measure, an elegant system. The mines were invisible to the enemy, findable by the owner, and the marking agent was itself invisible to anyone who did not know to look for it. The Allies did not learn about detectors until the occupation, when captured documents and interrogations revealed the program. It had been one of the most closely held secrets of the German Combat Engineering Corps. And it did not matter. Not at all. Because by early 1945, the Americans were not looking for mines with instruments of any kind. The Hürtgen Forest, November through December, 1944. If you have not encountered the Hürtgen in your reading, there is a reason for that. It is one of the war's least narrated and most costly engagements, fought across 50 square miles of dense pine forest along the Belgian-German border. The trees were tall enough to canopy the sky and close enough together that a man could not see 30 meters in any direction. The forest floor was a mat of dead needles, root tangles, and frozen mud. It was ideal mining terrain. The Germans used it accordingly. A battalion of American combat engineers entered a sector of the Hürtgen that their electronic detectors had marked as clear. The sweep had been thorough. The instruments had registered nothing. Under previous doctrine, the doctrine of 6 months earlier, that clearance would have been accepted and the infantry would have moved through. But the doctrine had changed. Revised standing orders, issued after the Italian campaign and updated again after Normandy, required that electronic sweeps be followed by manual probing regardless of instrument results. The engineers understood why. They had read the after-action digests. They knew about the Erdmine. They knew about the Porzellanmine. They knew their detectors could be beaten, so they got down on their elbows and knees in freezing forest soil and began to probe. They extracted 9,000 mines from ground their instruments had called clean. 9,000 from a single sector, every one of them ceramic, every one of them invisible to every detection device in the Allied inventory, and every one of them found by a man with a bayonet, working by touch, at a pace of perhaps 2 meters per minute. But the bayonet was only the beginning of the method. What made the system work was not the tool. A bayonet is not a system, but the layer of human perception that had been built around it, drilled into it, and documented across 2 years of institutional learning. The Americans called it, in their own informal shorthand, reading the ground. It was the accumulated craft of men who had cleared mines in Sicily, at Salerno, at Anzio, across the hedgerows of Normandy, and now in the frozen forests of the Rhineland. They had learned what mined ground looked like, not through any single lesson, but through 1,000 small corrections recorded and passed forward. A patch of soil that has been dug up and refilled does not settle the same way as soil that has lain undisturbed. The compaction is wrong. The color is slightly different, darker usually, because subsurface earth holds more moisture. Leaf litter that should be continuous has a gap, or lies too flat, or has been arranged rather than fallen. Drainage patterns around a buried object shift. Water pools where it should not, or fails to pool where it should. A thin crust of frost forms differently over disturbed ground than over packed earth, because the thermal conductivity has changed. None of this was visible to an untrained eye. All of it was legible to a man who had spent 8 months looking at nothing else. This knowledge had not arrived as a revelation. It had been assembled cumulatively, observation by observation, mistake by mistake, and captured in a chain of documents that tells its own story. After-action reports from Sicily noted that mines were often betrayed by drag marks where the burial team had approached. Field manuals issued before Anzio incorporated that detail. Revised editions published before Normandy added sections on soil compaction and frost patterns. Training programs at rear area schools were updated printing by printing, each edition absorbing the lessons of the latest campaign. A man arriving at the front in January 1945 carried in his training the compressed experience of every engineer who had gotten it wrong and lived to file a report since July 1943. The British, for their part, had invested in a parallel approach. Mine detection dogs, trained to scent explosive compounds in soil. The dogs were good. Under controlled conditions, they were impressive, but in the field, the comparison was not close. A trained human observer working with a probe cleared ground at 5 times the rate of a dog team, and with comparable accuracy. The dog could smell explosive. The man could smell it too sometimes, but more importantly, he could see the ground, interpret its texture, remember what a decoy pattern looked like versus a live minefield, and make judgment calls that no animal and no instrument could replicate. The German engineering corps knew that their mines were being found. They could see the cleared lanes. They could count the disarmed devices stacked at collection points. What they could not understand was how. Their instruments had been defeated. They knew this with certainty. Their own tests confirmed it. The ceramic casings were invisible to every magnetic, acoustic, and electrical detection method they were aware of. The magnetized gravel had poisoned the reliability of any sensor that might still be in use. Descartes ensured that even the residual traces of emplacement were masked. By every technical measure they could apply, the mines should have been undetectable. And yet the Americans found them, methodically, reliably, in numbers that made the minefields operationally irrelevant. The field reports kept using the same word, Ratlosigkeit, bafflement, again and again. It appears in after-action summaries, in intelligence assessments, in the handwritten notes of company-grade officers who had watched their careful work undone by men crawling through mud with pointed sticks. The bafflement was genuine. It was also diagnostic. The German sappers could not see what the Americans were doing because they were looking for a device, a counter-technology, a machine that answered their machine. They had built a problem that no machine could solve, and they were correct. No machine did solve it. What solved it was a culture, a system that tested, failed, recorded the failure, rewrote the manual, trained the revision, and then assumed, as a matter of institutional habit, that today's method would be tomorrow's vulnerability. The sensor had been a chapter. The bayonet was the next chapter. The reading of ground was the chapter after that. And behind all of it was the habit of writing the next chapter before the current one had been proven wrong. The Germans had built the perfect invisible mine. The Americans had built something the mind could not see. And the price of building it is what comes next. Cal Brennan is 22 years old, and he is sitting in a Higgins boat. It is June 6th, 1944, shortly after 6 in the morning, and the boat is one of several hundred churning through heavy chop toward a stretch of Norman coastline that Allied planners have designated with a name Brennan will never be able to hear again without tasting salt water. He is from Boise, Idaho. He is a combat engineer, and he knows the arithmetic. The casualty projections for the first wave of engineers had been briefed plainly because there was no way to brief them otherwise. The men clearing obstacles and mines on the beach would be working in the open, under direct fire, with no cover and no option to stop. The planners estimated that most of the first-wave engineer teams would be destroyed before they finished their assignments. Not most of the men, most of the teams. The distinction matters, because a four-man team can lose 2 members and still complete a lane if the survivors know the job well enough to do it shorthanded. The doctrine had been designed with that mathematics in mind. Brennan's partner in the boat was a man named Lyle. They had trained together for 8 months. 8 months of drilling the same sequence until it was automatic, because the planners understood that on the beach, under fire, nothing that required conscious thought would survive contact with the reality of the moment. Lyle was from somewhere in the Midwest. He had pitched minor league baseball before the war, and he had the kind of hands that made the delicate work of disarming a fuse look unhurried even when it wasn't. Brennan trusted those hands. The ramp dropped. They went into the water. What happened next took less than an hour, and it is not possible to reconstruct it cleanly, because the men who lived through it could not reconstruct it cleanly either. The accounts are fragmented, not because memory failed, but because the experience exceeded the bandwidth of sequential narrative. Things happened simultaneously. The tide was rising. Obstacles that had been visible during the approach were now submerged. Mines that had been planted at the waterline were now underwater mines, detonating against men who could not see them and could not have avoided them if they had. Lyle triggered one in the shallows. The mine took both his legs. Brennan and the remaining members of their team kept working. There is no other word for it. They did not advance or attack or charge. They worked methodically through the obstacles in their assigned lane because the lane had to be open before the infantry behind them could move. Lyle was carried to the waterline by a medic who had no evacuation route. He died before noon. A causeway inland, a road built over flooded marshland that the engineers would construct in the days that followed, was named for him. His name on a road sign in Normandy is the only permanent record most people will ever encounter of what he did that morning. 2 of Brennan's 4-man cell were killed. The lane was opened. Every assigned lane in their sector was opened, within the projected time frame, at the projected cost. The projections had been accurate. That is not a flattering anecdote. That is a confession, an acknowledgement that the institution had known what it was asking and had asked it anyway. The men on that beach were the product of the system this story has been tracing. The 8 months of drilling, the doctrine refined after the Rapido crossings, where the first encounter with ceramic mines had revealed that instruments alone would fail. The after-action reports from Sicily that noted how burial teams left drag marks. The field manual revisions that taught men to read soil compaction and frost patterns. The institutional habit of assuming that the current method was already obsolete and that the next failure was being engineered in a factory somewhere in Thuringia. Brennan and Lyle and the men in their team did not carry Dursky's magnetic anomaly sensor. Some engineer teams did, But the sensor was, by mid-1944, one tool among several, and not the most important one. The most important tool was the training. The layered, revised, failure-tested knowledge that had been compressed into 8 months of repetition, so that a 22-year-old from Boise could do the right thing on a beach in France without having to think about it. Because thinking was a luxury the situation would not afford. This is the verdict the story has been building toward, and it is worth stating plainly. Germany spent 2.5 years escalating mine design. Each generation of device was more sophisticated than the last. The Erdmine 43 defeated magnetic sensors. The Porzellanmine 44 defeated X-rays. The magnetized gravel defeated operator confidence. Dekird defeated even the possibility of residual detection. Every one of these innovations was a correct answer to the question the Germans believed they were being asked. And every one of them failed, not because the engineering was flawed, but because each device had been designed to defeat a specific instrument. And the Americans had moved the competition to a place where instruments were no longer the thing that mattered. The German escalation, with each step, drove the Americans deeper toward a method no materials science could counter. Strip away the magnetic sensor, and the engineers pick up a bayonet. Strip away the bayonet, if you could, and they would read the ground with their eyes. Strip away their eyes and they would read it with their fingers. The Americans had not built a better machine. They had built a culture, one that probed, recorded its failures, rewrote its doctrine, trained the revised method into reflex, and assumed as a matter of institutional habit that today's answer was already tomorrow's problem. The German sapper staring at the American engineers in March 1945 was not witnessing a technological advantage. He was witnessing the output of an institution that had been designed to learn faster than its enemy could innovate. His Ratlosigkeit, his bafflement, was not a failure of observation. It was a failure of category. He was looking for a device. There was no device. There was a system, and the system was made of people. And the people were made of training, and the training was made of the accumulated record of every man who had gotten it wrong and lived long enough to say so. There is an object that carries this whole story, if you let it. It is a bayonet, standard issue, 30 centimeters of steel, slightly tapered, with a handle designed to fit a rifle mounting, but more often held bare in a gloved hand. It has no circuitry, no magnetic coil, no power source. It cannot be jammed, spoofed, or rendered obsolete by a change in casing material. It asks one question: is there something here that the ground did not put here? And that question has no engineering counter. The bayonet found the mine that defeated every instrument. Not because the bayonet was superior technology, because it was not technology at all. It was the residue left when every shortcut had been stripped away. The thing that remained when there was nothing left but a man, and the ground, and the knowledge of what to feel for. The Germans had a word for what they could not explain. The Americans had a bayonet.